Yeah, thanks again. I very briefly remind you where we stopped. I showed you this result, and before we also started talking about the proof, but before I should do something, I just forgot for the 4 other hours. I should clearly mention that this theorem here is joint work with 4 other people. In particular, I would like to highlight Marius Wese. He's a PhD student, and he's alphabetically not first, but first on the paper because he really, I would say, this is majority of technical work. I swept a lot of it under the rug, but there are many, many technical things you have to prove and show in order to make all this formalism work. And he was really the main guy doing not only contributing to conceptual ideas, but also doing all the Cergy work. And then the other co-authors are Giovanna Marcelli and Domenico Monaco, friends from Rome. I will mention them soon in a different context, and Tadahiro Miao from Hokkaido University in Sapporo, who was visiting professor for 1 year in Tübingen while Marius and I started this project. Okay, so as I said, this is one of the main results I wanted to advertise and to explain, namely that if you have a gap Hamiltonian, this theorem is still assumed periodic, but I will show you, announce the result, or we can drop this assumption completely. So it's not really important. It's only important to make the definition of the object easy, but the result still holds. Without this assumption, if you have a Hamiltonian with an infinite volume Hamiltonian with a gap ground state, then it responds to external driving of this type. Any bounded interaction, whatever it is, we can do everything there. It doesn't have to be an external potential. And a linear potential in the one direction will lead to a current response, a current density in the one direction that is basically 0, meaning the system really is an insulator. So this is, I would say, the first proof in this context that an insulator insulates. So usually gap system and insulator are used synonymous. And the current density in the 2 direction is nearly linear in epsilon, so it's linear up to terms that are smaller than any power of epsilon. And epsilon, you should think here always as the strength of the external field. And the coefficient here is expressed in terms of the unperturbed ground state, W0. And because I will talk about this now, let me remind you that of the x1, x2 are the position operators, or the many body position operators. And this off diagonal is this off diagonal map, which is actually, if you remember, defined purely in terms of the Hamiltonian H. No. So this XOD, this net OD depends on H now. Okay. So I showed you. Oh, now this button also doesn't work. So I showed you the main, what is it, the computation, where in each step you have to do some work leading to the result. Where the final step I did not yet comment on, where we arrived here at a very similar expression for the whole conductivity. So this linear coefficient in this expansion of the current density is the whole conductivity. Expression for this coefficient, which almost looks the same as before, but now with this near state omega epsilon and a different off diagonal map. And what I would like to show you now is a lemma, which for some reason some people call Chern-Simons type lemma, but I could not explain why we call it like this, so I decided not to call it like this anymore, call it the variance lemma. That shows actually that we can here deform that this as a function of epsilon is constant, so we can just continuously go from epsilon to 0 without changing the value and get the result I claim. thing I did not tell you yet is how in this first step, we introduce here this off-diagonal map with respect to the nears, because the nears, I try to emphasize many times, is not a get ground state, at least it's not a get ground state of the Hamiltonian H epsilon, but it's a local, small local deformation of a get ground state. So how do we define a corresponding off-diagonal map here, which has the same property that we can, so this K, remember, is also 2, so the difference here is only that we put this OD on the X, that we can do this here without changing the value. And this is a very simple trick, which is extremely simple. It took us some time to realize that this is possible. So take any automorphism of the algebra that maps almost local operators to almost local operators, and the infinity Hamiltonian. Okay, I didn't write it with a gap ground state omega. Then we can define a deformed off-diagonal map, which I write as OD alpha, with this automorphism, in this almost obvious way. So we first apply alpha to A, then the original off-diagonal map, and then we apply alpha inverse. And by a trivial computation, which I not will run you through, is that the corresponding automorphically changed ground state will have the property that now in a commutator I can add OD alpha without changing the expectation. So this is a very simple algebraic trick, and this also works for these Lipschitz potentials and so on. So we can use this trick for omega epsilon, where now the OD epsilon, the alpha here is actually effective of our automorphism beta that maps the ground state to the near state. And remember, we said we constructed in such a way that this really acts locally on the ground state. So, and with this definition, I can state this invariance lemma, which says if you have a periodic Hamiltonian with a periodic gap ground state, and any co-cycle of automorphisms generated by a local interaction, then this expression here is invariant under such an automorphism, where we apply the automorphism to the state and to this off-diagonal. Okay, so that's this invariance lemma. So it doesn't change under applying locally generated automorphisms to the objects appearing in this form. Now I just realized that I took much more time than I expected, so I will not show you the proof. But actually, the idea is very simple. How do you do something like this? You take a time derivative on one side and show that the derivative of the left-hand side is 0. This is actually, in this case, quite a pain because, yeah, you have to worry about a lot of things converging. But in the end, that's all. So it's really constant along such curves where you smoothly deform the ground state and the corresponding parts of the position, off-diagonal parts of the position as well. Okay. That's, so to say, all I wanted to say about the proof. Now, I would like to discuss again some corollaries and consequences I mentioned already in the very first lecture, but maybe now it's easier to understand and to appreciate. In particular, this is goes in the direction of what Jan was asking or remarking this morning, namely, now we look at two quantities. One was this, what I called microscopic Hall conductance, having a small potential step within my material, and then along the step I have a microscopic current, and I look at the corresponding ratio between this current and the height of the potential step. I would call this a microscopic Hall conductance. The measured Hall conductance is something else. We have a macroscopic Hall bar, and we measure the current flowing through the whole Hall bar, and we divide by the voltage drop across the bar. So, as I emphasized in experiments, these are really macroscopic currents, macroscopic voltage. And so what we really would like to understand, what is the value of this observable, where now I didn't write the definition here. I didn't want to go too much into this. But JL is the current. You should think here in this context now, the current flowing into the upper half plane on an interval of length L. Now you say, how do you define this? I mean, since by construction, all these operators here are sums of local terms, there's not a completely unique definition how you define this, but no matter how you define it, the limit will always be the Hall conductivity we computed in the previous result, plus something which is smaller than any power of a sum. So actually, also this macroscopic quantity takes the same value, which is not surprising in a periodic system if you average over the current density, which is everywhere the same, and then you get back the density itself. Okay, but why am I emphasizing this? Because now for this observable, for this macroscopic current, one can also show relatively easily that the variance of this observable is 0, so that this has no fluctuation. So if you would look at, I really want to emphasize this, because this is, yeah. If you look at this, this average has also not half. Here, if you look at this quantity here, this would be a quantity which has fluctuations, quantum fluctuations of order 1, meaning the corresponding spectral measure of this observable with respect to that state would not be supported on this value, but it would be only on average quantized. But of course, in a macroscopic experiment, you don't see this. You only always get a deterministic value, and using the fact that we have a current density everywhere, we can compute these macro observables, and their variance goes to 0 or to infinity. This is, in the end, a very simple observation, because the current density observables at different locations will be very weakly correlated, so the correlations decay very fast, and this is just a consequence of law of large numbers or weakly correlated random variables. Okay, and again, I showed this picture just to remind you. I think this is what we really, why I say we prove a version of Ohm's law. We can, what you do in an experiment, you measure a macroscopic current, a macroscopic voltage drop, and you take the ratio, this slope here, as an approximation, as a measurement of the Hall conductivity, while the Hall conductivity, as it is usually defined, is just the slope at 0. And that this correction is very small tells you that doing the measurement really gives you almost a measurement of sigma h. Okay, another remark, which is hopefully now more understandable than it was in the beginning, is that actually this invariance lemma also tells us not only that we can deform from the NEA this expression back to the ground state, this double commutator expression, but that we can deform it using arbitrary automorphisms, in particular the automorphisms we constructed when having these families of gas ground state where the gas doesn't flow. This parallel transport spectral flow map. Along such maps, the whole conductivity is constant, so it is constant within gap spaces. If I define a gap space by being able to connect the two states with a locally generated automotive. Maybe there's a subtle point. Let me get into this. Let me just mention, I forgot to put this on the transparency. By the way, the value of this whole conductivity here actually depends only on the ground state and not on the Hamiltonian. This is maybe also important because, as I emphasized before, this OD map is defined using the Hamiltonian. So you could wonder whether different Hamiltonians with the same ground state could lead to different Hall conductivities. The answer is no. It's only if you take another gap Hamiltonian where omega 0 is the gap ground state off, you get the same expression. So it's really intrinsic to the state and not to the Hamiltonian. Okay, and a very simple observation, but again, you might wonder whether I was working on the lattice ZD, or now in 2 dimensions on the lattice Z2. Is it important that I take these very special directions x1, x2 that are aligned with the lattice? And the answer is no. While in the case of the step functions, this is actually not easy to prove that you get this for any kind of half plane. Here it is trivially true, because if you take any other 2 orthogonal directions A and B in R2 and take an electric field in the direction of A and then look at the response, the current density in the orthogonal direction B, you get exactly the same expression just by the fact that our expression is linear in both of the vectors. So basically, the fact that this expression is linear in x1 and linear x2 and OD and so on, all these maps are linear, means that you can rotate the 2 axes without changing this object at all. Which is also a nice thing about this formula, because in many cases you are often worried about what do you do with directions that are not commensurable with the lattice structure, so this doesn't play any role here. No matter where you put, how you put the electric field, you get always a perpendicular current, no matter what. And that will be actually also true for the case where you don't have periodicity at all. So the whole current response is really always orthogonal to the applied electric field. Okay. Yes, I mean of course you could also look at the current in a different direction, not orthogonal, induced by an electric field here. Then you would, of course, I mean, the component of the current in a different direction, I mean, you can compute from here just by geometry, but it's basically the result. No, sorry for going back and forth. This result really tells you see no current in the direction where you put the field, and you see a current proportional to sigma h in the orthogonal direction. You can compute the current response in any direction. And I'm not sure if I have any intuition why this should be like this, but probably the classical picture in the Hall effect telling you that the Lorentz force is always perpendicular to the direction would suggest this. But whether this is true in such a big generality, I would not have betted on before. Okay, so let me finally start discussing a bit of the previous literature. Specific to this result on the what I would now call Ohm's law. So Giovanna and Domenico proved similar results in 22 for non-interacting periodic fermion systems using this Neas approach. And there, because periodic there really means periodic, this was only possible for rational magnetic fields. But this was the motivation for us to look at this infinitely extended, actually continuum system. So, but I mean, you know, I mean, if you're one body continuum Schrödinger operators, I mean, you do Bloch-Floquet transform, and it's not so. They did not prove an adiabatic theorem also. They proved only existence of this Near state and this that there are no power law corrections to the ball response. And initially, my idea was, okay, I just take the proof and translate it to the many body setting, but then we take completely, and we developed a different. And I just heard last week a talk of a student of Domenico, this is not yet published, where they generalized this result for non-interacting continuum fermion systems to see also to irrational magnetic fields. So assuming a weaker form. Okay. Then the historical paper where it was first, there was the first mathematical argument why there should be no power law correction to this linear response was by Klein and Seiler in 90, where, and I will not have time to go into the whole setup, where they looked at systems, finite systems on a, this is not correct, but this is cylinder, there should be torus geometry on a torus. You have to put things on a torus, you don't want any boundaries at all. And they implement what basically our step function approach by having a time-dependent magnetic flux, which models a electric field. So through the cylinder. So this is what is called the flux spreading approach, or the Laplace argument. So they model this, and then they have to do some averaging. Let me not go into this too much, over an additional phase to introduce the problem. And after phase averaging and this flux spreading argument, which corresponds to an argument where you really pump charges in cycles, they show that the corresponding Hall conductance defined that way has no power law correction. And this is actually just a very nice application of the standard superadiabatic theorem, where you know that when there's no epsilon, only a eta, when the gaps are enclosed, when you do a smooth change or a smooth cycle, and in the end, in the beginning, the Hamiltonian is constant, there are no power law corrections to the deviation from the ground state. So if you're interested, I can tell you more in private. And these guys, again, they showed that this argument of Klein and Seiler also works without this additional averaging procedure. This was, in a sense, a bit of a big thing, because people always criticize, yeah, this is a nice result, but it uses this artificial averaging. How do you know that you can also do without? So, and they showed that you can do without, but it's still the response to spreading a single flux quantum to the so basically moving a fixed finite number of charges over one boundary in an arbitrarily large system. Up here, there is no, it's not really a physical averaging. There's no physical part. I mean, you could somehow interpret it as averaging about over the possible boundary conditions when putting this on a torus. So it's no, they don't do this averaging line and relative. This was the step from here to here to do it without averaging. And the additional averaging allows you to again make a topological argument, but you don't want to do it, and they show that you don't have to do it. Exactly. Exactly. So that's basically what you have to do in that. But what I want to, maybe I should show the next pictures. What I would like to emphasize again is that these approaches really do what we did in this step function approach. You put locally a small electric field or small step in your chemical potential. You can actually also clear this over the whole circumference of the torus, but then the applied field will be of order epsilon over L. Okay? So you will never see in this approach macroscopic current flowing in this system. Because to see a macroscopic current, you have to close the gap. And this in this approach you cannot do because you want to apply the usual adiabatic field. While in our approach, we still have a small field, so a small slope, but over arbitrary distances, so we can see macroscopic current. Good, this was lecture 4, and now I close with a few further remarks, unless there are questions. And I would like to come back to the question of gapped phases of this weakly interacting Hochstadter model. So just to remind you of this model, the non-interacting one is just the second quantization of this one-body discrete Schrödinger operator, where the HB is the phase factor times the kernel of the discrete Laplacian. You can take here also this more general discrete short range operators. Important is that the B field is introduced by these additional phases. Okay. And as I also mentioned in the first lecture already, it is known that for such a non-interacting system, the gap is stable, meaning that if you add to this non-interacting system a small, so lambda is the coupling parameter, small perturbation by being also a sum of local terms, then for lambda sufficiently small, this many-body operator will still have a gap ground state. Surprisingly, it's not even for this system known whether this is the unique ground state. So if anybody has ideas how to prove that uniqueness is also preserved under small perturbations, I would be very interested. So this is one of the reasons why we never wanted to assume uniqueness of the ground state, because it's not known in many interesting positions. Okay, and now I added here an additional reference. So actually, for periodic systems, it also follows relatively easily from the slides of the area. So again, just to remind you of the picture before we go in more detail, this is the colored Hochstadter butterfly, and I should also have given credit the first time I showed it to Cergy and Cergy, who produced these pictures many years ago. As you can see, this is 2001. And where I also learned that one can interpret this picture as a phase diagram. Different phases. Just to remind you, on the horizontal axis, we have the B field. On the vertical axis, this is the energy axis. So this is depicting the complement of the spectrum of this one-body Hochstadter operator. So at 0 B field, where here the spectrum is just an interval. Okay, one interval is the spectrum of the discrete Laplace. And if you change B, you will have this spectrum will split into Landau levels. These are the boundaries between the phases, between the colors. At least at the edges, you see this really looks like Landau levels. And yeah, but what's here colored is the complement of the spectrum, the resolvent set in the two-dimensional plane, which is open, also as a subset of the two-dimensional plane, and the colors are the turn numbers of the vector bundles over the torus defined by the band below. If I go to point here at 1/3, I have 3 intervals. At every rational value, these bands below a point in the gap define a vector bundle which has a turn number and which Fowler shows is related to the whole conductivity of this model if you put the magnetic field here and the chemical potential at the corresponding energy site. Okay, so what I told you before, this shows that the gap is stable, so that we basically can extend this phase diagram. Let's think of it in a third direction, in a lambda direction, when we add interactions, and we will get still open sets where the gap stays open. Okay, wherever I'm here in this picture, if I add a small interaction, if it's small enough, the gap will not close. But you can also ask, is the gap stable, or is also the hole conductivity, the coloring, will that also be stable? Will you get the same hole conductivity if you add interaction? And the answer is yes. And this was first really proved in a paper by Alessandro Vieri and Marcello, the same paper I mentioned before, where they directly showed, starting from a non-interacting model, adding a sufficiently small, everything periodic interaction, then the whole conductivity does not change. However, I mean, they really assume periodicity, but then it's easy in a review paper. Alessandro mentioned that this implies in particular that this is also true if you add magnetic fields, which are rational. But of course, we can now ask, what about irrational values? And you would think, and it's true, that you can now apply our results on constancy of the hole conductivity in gap spaces to conclude immediately that the colors extend continuously or constantly also for irrational values of C. So can we apply our results to show that sigma h is constant in these specific gap spaces? And the answer is yes. And I'm mentioning this because there is a caveat to it, which I think is interesting. The answer is yes, but I mean, in a straightforward way, only in the mu and the lambda direction. What I want to say is if you change the ground state in this picture, here, in the mu direction, that's the vertical direction. If you move in the vertical direction, or if you add a small perturbation, then lambda direction basically goes out of this plane here, then you really have one parameter family of states that are automorphically equivalent. So changing the mu will really lead to such a nice path in the space of ground states so we can apply our result on automorphic equivalence. So we can easily show that this picture is stable in the mu direction, also with lambda, and in the lambda direction. And particularly, we can immediately recover the result of these three guys. But then we also thought we should be able to show that we have automorphic equivalence in the direction when we vary the magnetic field. So in this picture before, everything, the colors were constant, and then changing the magnetic field as well. But then you realize that if you look at the corresponding spectral flow, this automorphism generated by changing the Hamiltonian, you remember the generator of the change of the ground state was, at that point, I denoted it by h dot, the derivative of the Hamiltonian with respect to the parameter. So if we now look at our Hamiltonian and look at the derivative of the Hamiltonian with respect to the B field, we realize, so this is one of the interactions for the set xy. This is our non-interacting Hamiltonian. If we take a B derivative, that's very easy. We get this expression here. And we see that we get an interaction which is not bounded anymore. It's still local. These terms remain perfectly localized, but the coefficient grows linear in the two directions. Of course, this is very well known that changing a constant magnetic field and an operator is a very singular perturbation. But in particular, you see it here again, it does not allow us to apply our result on automorphic equivalence in the B direction. So you could ask, is it really a good definition to say two states are automorphically equivalent if I can connect them by an automorphism generated by a uniformly local interaction? Because then this definition might not cover different B fields, although I would say from this picture, this should definitely be one phase if I move here in the B direction. So there are two possible answers to this, and I'm mentioning this because I think this might be an interesting problem, and I really don't know what will come out of this. I mentioned this, and the first reaction by people working in this field was, yeah, but automorphic equivalence plus stacking, trivial system. So if you never heard about this, I will not explain it now, so that there may be a way out of this, but I don't think so. I think one should try to allow automorphisms generated also by such interaction. Automorphisms generated by interactions that have linear growth that are sum of local terms, but the norms of the terms can grow linearly. Now you may ask, is it true that such interactions generate automorphisms, that they have a thermodynamic limit? And surprisingly, this question was, as far as I know, and I asked people, talked to people, unknown, and I didn't write this down, and we managed to prove actually that also such type of interactions with linear growth of the local term generate global automorphisms in the thermodynamic limit. And the intuition is not so different from if you look at ODE. A linear ODE, where there's a vector field in your ODE, so the possible local velocities can grow linear in space as still global solutions. It can go exponentially fast to infinity, but not in finite time. And this is actually here exactly the same thing. If you leave Robinson velocity, the local leave Robinson velocity of the interaction grows only linear, you still get a well-defined automorphism to dynamics on the total algebra for all time. And then we could also show that for these kind of automorphisms, our formula for the Hall conductance is still invariant. So in the end, we could lift this automorphic equivalence also in the B direction. So, I mean, the upshot is, I mean, this is actually something we had in the other paper, but then it was so long, and after refereeing, we kicked it out, and now it's not yet in the archives because nobody wants to write the introduction. We now can show that for Hochstatter type models, if you are initially in a gap of the non-interacting model, there is always an open ball in this parameter space, mu, b, and the small interaction, such that within this ball, the Hall conductivity is constant and quanta. So you get the quantization. Using this approach, you get the quantization not by proving again some sort of, which is also people also do and try by looking directly at this many-body expression for the Hall conductivity and somehow show that it's quantized, but just by connecting it to the non-interacting model where it's already known and easy to see that you have quantization. Okay, and this brings me to another remark. In general, for this many-body object, it will not be true that the Hall conductivity is an integer multiple of 1/2 pi. So that's the thing. It will not be an integer. In particular, there are shortly after not too long after the observation of the quantum Hall effect, and saw also plateaus in these graph I showed you for the Hall resistance at fractional values of the existing constant, which is then called the fractional quantum Hall effect. And in particular, our results are completely general. Gap implies a well-defined linear response that is constant in gap spaces, that is very stable to small perturbations, but it doesn't say anything about the value. So, and in general, it will not be integer. It would, yes, it applies to any gap model that they have a gap. That would be very nice. There are models, but not of the type of the Hochstatter model yet. So where you have fractional quantization. I don't know enough about the model. Not that I know, but that I think that's not a problem of the result, because I think the results cannot be more general, except if you want to include long-range interactions and screening and stuff, but this is also not done in models. Yeah. I mean, this is the whole other story, and I'm not really an expert about this, but I would expect that eventually people will come up with models for fermionic systems where you can also see fractional quantization. Exactly. And that they are very typically not all fractions you will see, but very specific fractions. And okay, this is maybe let me. So what you would expect, I mean, I think this is what the very naive physics picture would be in if you add to a non-interacting system small interaction. You will, I mean, this gap is stable, but the stronger the interactions, the more this picture will be deformed, and eventually the idea is that strong interaction can split the Landau levels into sub-levels, and then if you are in a gap of a split Landau level, then you will see fractional quantization. So you will see the idea is, I mean, all the rigorous work, assume that expect that fractional filling of Landau levels is the reason for fractional compensation, and that you can see fractional plateaus at fractional filling because the interaction with split will produce small gaps in the Landau level. Here you see only integers. All the colors are integers here. But if you just pretend that you fill one of these, I mean, this would be still a Landau level at a very strong flux. Here, if you would pretend that you could fill this to a fraction and then introduce a gap by hand, you would see a fractional compensation. That's cool. Yes, because I was sitting every evening until late to do these transparencies, and you're right. I mean, let me. Yes, I think I said this in the beginning, but I should have repeated this. The colors are integers. 1, 2, 3. The warm color is positive, and the blue color is negative. So actually, if you add up all the colors from here to here, white is 0. They add up to 0. And this is because the total block band here is trivial topology, and you split it into subbands with different Chern numbers, but the Chern numbers have to add up to 0. Okay. So what did I want to say next? Yeah, I mean, there is a result which I have to admit, I mean, we tried to fill in what we thought were gaps, and we didn't really succeed to fully understand this result by consistent Tupenko. But I think it's in the end it's correct. Is that non-interacting systems, not only the Hofstadter model, but non-interacting systems almost like maybe more generally, I don't know, maybe it's equivalent systems with an non-interacting systems, or more generally, systems with an invertible ground state. I will not have time to explain what this is. For those, sigma h is always an integer multiple of 1/2 times. So if this result is correct, then we can show that whenever our ground state is invertible, you have integer compensation. But this is basically, as far as I understand, only expected for ground states that are in a gap phase that contains also a non-interacting model. For exactly the phases of the Hofstadter model we discussed. Okay, and let me use the last 10 minutes to say, to announce the result, which hopefully will appear soon. Namely, that we can do the whole, this response to constant external fields also without the periodicity assumption, which at least to me was surprising, although I will now tell you that a posteriori is not surprising. First, recall that the construction of the NEA, so this general adiabatic theorem, nor the result on the microscopic response, where we had these only these step functions, required any periodicity assumption or homogeneity assumption. This was only based on the gap. We didn't assume anything else. Okay. So the question is, can we now also show this macroscopic current response result, assuming only the gap and no periodicity? And the obvious problem is, and that's why we in the beginning didn't need to think about it, is then we would have to worry about defining the current density. So how is the average over the current expectation? How do we show that it's well defined without assuming periodicity or some kind of homogeneity? Usually you define these averages using some kind of homogeneity, ergodicity, whatever. If you don't assume anything, there is no reason why this limit should exist. In particular, independent of the Van Hofe sequence we take here. And it turns out that this limit does exist almost. And the reason is because what one can show is that if we, there should be no bar here, I'm sorry, that this equality we had here between the averages, we can show for the limit. I mean, basically, we can show this term-wise that the difference between the terms goes to 0 for lambda to infinity, up to something which is our error here. So there should be no bar here. So if I average on both sides of my equation I want to prove over finite volume, then I can prove that these two limits agree, assuming that this limit here exists. And now there should also be no bar here. And now actually it turns out that without assuming any homogeneity, this limit always exists. So averaging the expectation of this commutator restricted to finite region lambda, so no bar here, that's this expectation, dividing by the volume and taking lambda to infinity. This limit exists for every van Hofe sequence and it's independent of the sequence and gives back the whole conductance of the conductivity. So basically, showing that this limit exists allows us with the same proof to show also that this limit exists. So the argument is a posteriori quite simple. So here we have a commutator of x position operators, but we can write a position operator restricted to a region lambda, and then we extend this just constantly. Remember, then this is the multiple of the number operator, which commutes with the local terms of the Hamiltonian. We just approximate this, and we are on a discrete space, so this is not an approximation. Sorry, we just write this thing here as a sum of shifted step functions. I don't write down the formula, but it's obvious that we can do it. And then we know that the expectation for all these commutators of step functions is always the same at each point in the lattice. So we have then exactly number of points in lambda crossings of these step functions. We divide by lambda, so we get the value for one back and we prove this. So basically, the only reason why this is not identically why you have to take a limit is, of course, because when you at the boundaries here and here, you will make there will be errors, and but they are boundary terms divided by a volume, so they vanish in the large volume limit. So this is the idea that allows you to prove. I think I put the general theorem. This is now again with Marius and Tadahiro, that only assuming locality of interaction and a gap ground state, the current response is almost linear in the following way. Namely, we can, because of this O epsilon infinity, we can still not show that this limit exists for the current density, but it follows that the difference between the lim sup of this and the lim inf of this is order epsilon infinity. So there might, you can still, in principle, envision situations where the limit does not exist, but it will fluctuate on a very small scale. And if I define now the current density in the near side just as since they are so close together, I just define it as the mean value of the lim sup and lim in. Then for that current density, we get back the initial result. What do you mean in the Van Hofe sense? I mean, this is for every Van Hofe sequence, so you have to, for every sequence of lambda that eventually contains every point, you will maybe I misunderstood the question. So. Yeah. No, I mean, it should be a sequence of lambdas that eventually covers all of that too. So, this is actually also true in ZT, but there are no examples in ZT of such systems. So, I mean, this is just to emphasize that you don't have to take a specific sequence of boxes, let's say. So you can take a sequence of boxes, but it doesn't matter where you start, where your center is, or you can take circles or rectangles or other crazy things. It just has to eventually, I mean, contain every point. It needs to be a, what do you say, a monotonically increasing sequence of sets that eventually contains every point. And then you always get, for every such sequence, this system is all sum in infinity, and the mean value will satisfy. So, yeah, and that shows that the gap assumption is enough to guarantee that the current response is everywhere almost the same. So no matter how you change the material, you will not be able to change the current response without closing the gap. So you don't need any kind of coding. Okay. Now, this was actually for non-interacting systems, this was known, but I didn't know it. Otherwise, we would have maybe not written the first paper in the periodic case, but immediately this paper. Actually, I just realized later, or in this case, I was told by these people who could have known, that in an appendix of a very influential paper by Elgar and Schenker, they show this, that this quantity here has an average in the non-interacting case for lattice systems without periodicity or ergodicity, only assuming the gap. But it's hidden in an appendix and not mentioned in the introduction. So yeah, I mean, they always look at one-body operators and the Fermi system. So they really look only on the one-body level. They don't, and there, I think there's no point then to write it as well. Exactly. Exactly. Like the non-interacting Buchstaben. And okay. So, and these guys actually showed it also for continuous models. But again, also in an appendix, and also it's not mentioned in the introduction or anyway. So just a tip, if you have a nice result, don't put it in the appendix. Or at least mention it in the introduction. Okay, yeah, then I have to try it next time, yes. Okay, so this is perfect timing. I knew that I would be slow again. So let me just end. The summary and conclusion is very simple. I think this whole program shows for under really only two assumptions, short-range interactions and the gap, one can show that such systems are insulator when it comes to charge transport in reaction of constant external fields. We show that the transversal current, the whole current satisfies Ohm's law, at least for small fields. And yeah, one thing from the experimental point of view, which I also like, is that the macroscopic hole conductance can now be defined, computed, and shown to be really a deterministic observable that is constant within gap spaces, meaning it is really extremely, I mean, it's applying insensitive to all kinds of perturbation that do not close the gap. And that explains the universality we see in experiments. Thanks a lot for your 5 hours of attention and for the many, many great questions and comments.